All right, welcome back again, everybody. Today we're doing section 14.6, and this is where we're going to get a very important and very powerful tool known as the gradient and the gradient vector. We're also going to learn about directional derivatives, which are basically like derivatives in any direction, you could say. So let me pull up the slides and we will get started. All right, 14.6. So here's the overview. We're going to talk about what the directional derivative is. We're going to define it. Then we're going to define what the gradient vector is. Oop, one second. There we go. There we go. Then we're going to extend these definitions to functions of several variables, like we have been in the, it's like a running theme throughout the course. We'll talk about maximizing the directional derivative, and then we'll finish up with tangent planes to level surfaces. Okay, so let's start with this, the directional derivative. And let's just stick to 2 dimensions for now. So we'll do a function of 2 variables. So maybe I'll say 3 dimensions. If you remember from the previous section, the partial derivatives, f sub x and f sub y, are these right here. And this is how we define them provided those limits exist. So basically speaking, those derivatives are the derivatives in the direction of the basis vectors I and j. So when you think about the partial derivatives of a function, you can think about them like that. It's basically the derivative in that direction, except the direction is I or j. So that's what the partial derivatives are. However, we can extend this notion of taking a derivative into any direction, and that's actually what we call the directional derivative. So let's make sense of that. Suppose we want to find the slope of a tangent line to a surface S. We'll say this is the surface. The surface is given by f of x comma y, and we want to find the slope of the tangent line at a point in the direction of an arbitrary unit vector u. So quite literally, if you can think about this picture for a minute, we want to find the slope of this tangent line in that direction, and the direction doesn't happen to be in the I direction or the j direction. It's just some arbitrary direction given by a unit vector. That's what we're going to do. So the vertical plane that you see pictured here, it passes through P in the direction of U, and it intersects our surface in a curve C. So let me zoom in again here. You can see that when you intersect the surface with this plane, you get a curve, right? You get a curve, and we're finding the tangent line to the curve at this point. That's the idea. Okay. So the slope of that tangent line is the rate of change of z in the direction u. So how are we going to develop this and get a formula for this? Well, we're going to pick another point on C. We'll call it Q. So here's Q, here's P. And we're going to project those points down onto the XY plane. So if you kind of see here, let me zoom in a bit, there we go. We're projecting this down to here and projecting this down to here. That's what we're doing, okay? Then what we know is that this line right here, maybe that vector I should say, is going to be parallel to the vector u. So what that means is that there has to be a scalar such that this vector can be written as some scalar multiple of that unit vector u, which we'll write as HA comma HB. And you can kind of see it down here as well. So there we go. Okay, now with a little bit of finagling, we get something cool to pop out here. We can write the difference between x and x naught as HA. So remember, this is x naught, y naught 0, and this is x, y 0 right here. So what we can do is we can write x naught minus y naught, which is this, as HA, and then y minus y naught as HB right here. But then just through a little bit of algebraic manipulation, we can re-express x as x naught plus HA. So we can express, this as this, oops, sorry, wrong way. We can express this as this plus this. That's the idea. So just getting that distance right there. Now we do that for both x and y, and then we can rewrite this, this difference quotient like so. So delta z is just the change in z, so z minus z naught. H is h. Remember, z is f of x comma y, and f of z naught is f of x naught comma y naught. So we get this. But we just re-expressed x as x naught plus HA, and we just re-expressed y as y naught plus HB. So this is very, very similar to what you did in 1 dimension when you were first learning about the derivative back in Calc 1. It's basically the same idea, except now there's 2 different dimensions. And then we have a, a surface that lies in 3 dimensions. So this is what we have for the difference quotient in that direction. Thus, we can take the limit as h goes to 0, and we get the definition of the directional derivative in 2 variables. So let's read it out. The directional derivative of f at some point in the direction of a unit vector u given by a comma b is denoted by this symbol, and it's basically taking the limit of this difference quotient. So this little, let me zoom in on this a bit here. So this symbol right here, this d sub u, this is like saying take the derivative of f in the direction of u. So this is that derivative notation, or that differential operator notation showing up, except now instead of this being an x or a 1 or a 2, it's a u, because you're saying take the derivative in that direction. Here's how you do it. And then sometimes, just as a nice shorthand, we'll abbreviate it as f sub u, just like we did before when we had f sub x and f sub y. And again, this is all assuming that these limits exist. So if this limit doesn't exist, then you can't have a directional derivative in that case. Okay. Yeah, so just like before, using the actual definition of the derivative can be cumbersome. So in practice, what we like to do is we like to have a shortcut, usually some kind of a formula or some like set of properties that we can use. The same thing is going to happen here. In practice, we often appeal to the following very, very cute, very, very concise theorem, which gives us this formula here. So here's the theorem. If f is a differentiable function of x and y, then f has a directional derivative in the direction of any unit vector u, and you can write the directional derivative like this, which is just really, really cool. So if you want to find the slope of the tangent line at a point in the direction of u, you basically compute the partials at that point, multiply x by the a, or the first component of the unit vector, multiply this by the second component of the unit vector, and that gives you the directional derivative. Okay. Oh yeah, there you go. This is basically the same thing that I was saying, but kind of restated in a different way. So if you want to do the directional derivative of a function in the direction of u, you scale the partial derivatives by the components of u, respectively, a and b, and then you add the results. Okay. So let's prove this theorem, because remember, we had the definition of the directional derivative, but let's prove that this theorem is actually valid. So this is a nice proof to walk through and just to see how this thing works. So first thing we're going to do is we're going to define a function g of a single variable, and we're just going to call g of h equal to f of this stuff. And the thing I want to emphasize here is that x naught is a constant, a is a constant, y naught is a constant, and b is a constant. So the only thing that is changing here for this function is h at the moment. Now we're going to use the definition of the derivative for a single variable function and just do the limit of the difference quotient. So g prime of 0 is equal to this by definition, but remember that g of h is equal to this by the way that we wrote it down, and g of 0 is going to be equal to f of x naught y naught, because if we plug in 0 up here for h, that disappears and that disappears, and so we're left, oh, and this would be a 0, there we go. So now you're getting f of x naught y naught, but this right here is quite literally the definition of the directional derivative. So we're getting that this derivative here is the directional derivative at x naught y naught in the direction of u. Okay, that's the first step. Now, what we're going to do is we're going to write g of h equals f of x y, where x is equal to x naught plus ha, and y is equal to y naught plus hb, kind of like we did a moment ago. And then we're going to use the chain rule on this. So by the chain rule, the derivative of this is going to be equal to this. And let's just walk through it just to kind of refresh our memories of how the chain rule works, right? So f is a function of x and y, but both x and y are functions of h, right? So if I want to do the derivative of this function with respect to h, I got to use the chain rule. It'll be the derivative of f with respect to x times the derivative of x with respect to h. That's this right here. And then we're going to add the derivative of f with respect to y times the derivative of y with respect to h. And that's this right here. And then we're going to add the results, right? But remember, partial f partial x is just the partial with respect to x. And dx dh, this we can actually compute directly. So look at this formula for a minute. If you differentiate this with respect to h, what do you get? Well, that goes away, and you're just left with a right there. Do the same thing for this term right here. Partial f partial y is the partial with respect to y, and the derivative of y with respect to h is just going to give you b. So there we go. So now we have that g prime of h is actually equal to this. Now if we set h equal to 0, so we're going to set h equal to 0 here. If this is 0, this term disappears, and this term disappears. So then x equals x naught, y equals y naught, and now we can go and sub in to our previous formula there. So g prime of 0 is going to be equal to this, but we also just showed that this is equal to g prime of 0. And there we go. So now we've shown that the directional derivative in the direction of u of f is equal to this right here, which is cute. It's just a really, really cute result. Cutting through all of the cutting through all of the mess and all of the proof, really it's just saying if you want to find the derivative in any direction, you do your partials with respect to x and y, and then you scale them by whatever the components of that unit vector are, which is really, really nice. We're actually going to get another very, very concise formula for this in a few slides here, but maybe if you want to ponder it, maybe this right here. Take a look at that structure and see if it just looks a little bit familiar to you. All right. Now, from this, we actually get another even cuter result. So here's a corollary of that result. If the unit vector u makes an angle theta with the positive x-axis, then that means that you can write the unit vector in terms of cosines and sines. So this will be cosine theta, this will be sine theta, and now we can substitute those values into our previous formula, and we can write it like this. Cool stuff. So the directional derivative in the direction of u is the partials, and if you happen to just know the angle that u is making with the positive x-axis, then you can just multiply by cosine theta, sine theta, instead of the components themselves. Cool stuff. All right, let's practice. Let f of x comma y be equal to this polynomial here, and we're going to let u be the unit vector that's given by this angle. So this is the angle that u makes with the positive x-axis. So what I want you to try on your own is to find the directional derivative and then compute the directional derivative in the direction of u at the point 1 comma 2. So do it in general and then evaluate it at 1 comma 2. So first, just think about how you're going to start. What's something you might do first? All right, and now say something out loud. This is the first time, so say something out loud. Give your brain that feedback, just to give give yourself to wake yourself up and give you that feedback. All right, and now try to work it out on your own. Compute the general derivative, directional derivative, and then evaluate it at 1 comma 2, and we'll do it together in a moment. All right, here we go. So first things first, we got to compute the partial derivatives. So hopefully everybody's pretty comfortable with that. Remember, to compute the partials, you're just holding the other variable as a constant and differentiating with respect to the given variable here. So f sub x is equal to this, f sub y is equal to that. So using that theorem, or really using that corollary that we just talked about, we can write the directional derivative in the direction of u at any point as this formula right here. We just computed these up above. And cosine of pi over 6 is, let's see, root 3 over 2. And sine of pi over 6 is 1/2. And then now we can just simplify at our leisure, however we want to, if we want to. But this is the directional derivative of f in the direction of u at any point. So this will give us the directional derivative at any point. Right, now to evaluate it at 1 comma 2, we simply plug in 1 for x and 2 for y, and simplify at leisure, and this is what we get. All right, so just again to kind of like reconnect what we just did here, what we did was we found the slope of the tangent line to the graph of this function here at the point 1 comma 2 in the direction of the vector u, the vector u that makes an angle pi over 6 with the positive x-axis. So that's what we just did. We did actually find the slope of a tangent line here. That's really what this thing is. All right, Now, coming off of this, we're going to talk about the gradient vector. So you might have noticed when I had you ponder that formula just a couple minutes ago, you can actually express the directional derivative as a dot product of two vectors. So it's this structure of the dot product showing up over and over again, right? This thing times this plus this thing times this. Well, if we scoop these up and make a vector out of them, and then we scoop these up and make a vector out of them, we can rewrite this as just the dot product. That's pretty much it. It's the dot product of these two vectors, and this, of course, is the vector u, our unit vector that we want to take the derivative in the direction of, right? So this vector right here, the vector of the partial derivatives, is extremely important, and so it has a special name. Maybe you can guess what it is. It's called the gradient vector. So the gradient vector, simply put, is the vector of all the partial derivatives. That's the easiest way to make sense of it. Um, Let me read out the definition and point out a couple of things here. So first of all, if f is a scalar valued function, meaning it spits out a scalar of two variables x and y, then the gradient of f is the vector valued function given by this symbol right here, a little upside down triangle. And it's literally defined as the vector of the partial derivatives. So that's what it is. When you think of the gradient, just think of a vector that contains all the partial derivatives of your function, whichever your function is. This symbol here there's a lot of ways you can pronounce it. You can pronounce it del f or nabla f. If any of you are learning LaTeX, this is the command for this symbol. A lot of times people will just say gradient or grad f, just because to emphasize that we're talking about the gradient. So all of these are acceptable pronunciations, and this is also another acceptable notation, grad f. Now, with this notation, the directional derivative becomes really, really concise and really, really simple to follow. It's just this. So the directional derivative of the function f in the direction u is just the dot product of the gradient and that unit vector u. Maybe I should do that backwards. The gradient and the unit vector u. Super easy to do, right? Compute your partials and then take that vector, the gradient vector, and dot it with u. That's all you got to do. Okay, so this is one you're going to try on your own again. So given this function, this mess right here, I want you to try to find the gradient of f, okay? So think about what you would do first. You may not have to think for very long. Okay, say something out loud to yourself that's going to help you remember what the gradient is. All right, now compute it. Compute the gradient of this function, and we'll do it together in a moment. All right, here we go. If we're computing the gradient, all we really need to do is compute the partial derivatives, the partial with respect to x and y, and then make a vector out of them. That's it. So the partial derivative with respect to x gives us this. The partial derivative with respect to y gives us this. And so that means that the gradient of f is just the vector that contains these two partial derivatives. I didn't go through all the work on this part, but just remember that you'll have to use like product rule, chain rule, that kind of stuff. That's all fair game for any kind of derivative. Okay, let's do another example. See if you can find the directional derivative of the function given here. This is a polynomial at this point in the direction of this vector right here. So once again, I'll throw up the thinker here. What do you want to do first? Think about it. All right, now speak up. Say something to anybody, your dog, your friend, yourself. What are you going to do first? All right, now try to work it out on your own, and we'll do it together in a moment. All right, the fun stuff. See, this is kind of fun, you got to admit. You're just doing a bunch of derivatives and making a vector out of them. It's kind of cool. All right, so first we need the partial derivatives. So we need to differentiate this with respect to x, and then we need to differentiate this with respect to y, and that will give us our gradient vector. Boom. There it is. Oh, in this case, I wrote it in terms of the basis vectors I and j. You can write it in any form you want. You can use the angled brackets. You can use these. Just be able to transition between both of them. We're going to use both of them willy-nilly throughout the course. Now, because we just want the derivative at this point, we're going to evaluate the gradient at the point 2, -1, and that simplifies to this. So this is the gradient evaluated at that point. Now, before we dot it with v, take note that v is not a unit vector. So it is important that you use a unit vector here, because if you don't use a unit vector, then you're going to be introducing these extra scaling factors that we don't want. So make sure that you normalize your vector first if you're not already given a unit vector. So what do? We need to find the length of v and then divide each component by its length. So here we go. Length is not too hard. It's square root of 2 squared plus 5 squared. So 4 plus 25, 29. So square root of 29. And then this is the unit vector now. Now that we have the unit vector and we have our gradient vector, we're going to dot the two. Here we go. Dot the two together. Simple calculation. And remember, when you dot two vectors, you get out a number, right? You get out a scalar. So when we do this, we get out this, 32 over square root of 29. And again, just for intuition, just to keep in mind what we actually did, we just found the derivative of f at the point 2, -1 in the direction of u. And we found that that derivative, the slope of that tangent line, is this. So that's the slope of the tangent line with respect to z. Okay. All right, so of course, all of these concepts can be extended to higher dimensions. So you should always have this on the back of your mind, like what would this look like in 3 dimensions, 4 dimensions, 5 dimensions, n dimensions, right? So here are the same definitions, but just stated in generality. So what is the directional derivative of a function with n variables? Let f be a scalar valued function. We're going to say that these are the n variables that it's a function of. Then the directional derivative of f at the terminal point of the position vector x naught in the direction of a unit vector u is simply given by this formula, which is to be expected because it is quite literally the same formula. The same formula. The only difference now is that you've got n variables, and those n variables are encapsulated in this one vector. That's the idea, provided the limit exists. Okay, so then what is the gradient vector? Gradient is still the same thing. So let's say you've got a function of n variables. We're going to let x equal this vector, a vector of just all of the variables from 1 to n. Then the gradient of f is still a vector valued function, and it is the same thing. It's just a vector that contains all of the partial derivatives of f with respect to each one of those variables, x1, x2, x3, dot, 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 all the way up to xn. So same idea, just more dimensions. And then with this notation, we can still rewrite the directional derivative very concisely. Gradient of f dot u. That's it. Cool stuff, cool stuff. All right, so now that we have the gradient vector, there are two very important questions that we want to ask, and just about directional derivatives in general. So remember that the directional derivative gives you a rate of change at any point in any direction u. So we have a couple natural questions to ask. One is, what is the maximum rate of change of f at any given point? And two, in what direction does f change the fastest? So in other words, which way would I have to turn so that f would be increasing the fastest? Which way would I face, right? And then aside from that, how fast would I be ascending, you could say, right? Those are the big questions. And those are going to be answered with this theorem, which we're going to prove in just a minute here. So suppose f is a differentiable function, real valued function of 2 or more variables, doesn't have to be 2 variables. Then it turns out that the maximum value of the directional derivative is the magnitude of the gradient vector, and this maximum value occurs when u has the same direction as the gradient vector. That's what this says. So in other words, the big idea, the gradient vector, grad f, gives the direction of fastest ascent. And the rate of this ascent is literally the magnitude of the gradient vector itself. So this is a huge idea. This is like one of the biggest takeaways that you want to have from the gradient vector. So I'm going to throw up the thinker here again. And I just want you to stare at this and kind of mull it over in your brain a couple of times. Okay, now I want you to actually say it out loud to yourself. So speak these two sentences out loud just so that the big idea of the gradient vector settles in. And then we're going to prove it. All right, here we go. So let's prove that this is the case. So the proof is actually very quick and cute. There's a lot of cute proofs in this section. All right, so what is the directional derivative of f in the direction of u? Well, from that earlier result we had, we know that we can write it as the gradient dotted with u. But from this equivalent formula for the dot product, we can write the dot product as length of the gradient times length of u times cosine theta, where theta is the angle in between the two vectors. All right, but the length of u is 1 because it's a unit vector. So really the directional derivative is written like so. So the directional derivative in the direction of u is the length of f, or sorry, the length of the gradient of f, or the magnitude of the gradient of f, times cosine theta. All right, now the maximum value of cosine theta is 1. And this occurs when the angle is 0. So basically when the two vectors are pointing in the same direction, that's when cosine is maximized, right? So that means that the gradient and the unit vector have to be pointing in the same direction if you want to maximize the directional derivative. But that would mean that the maximum value of the directional derivative is just the length of the gradient vector itself, because then this will just become 1, right? That'll become 1, and that's the proof. So there you go. That's it. What's also nice about this is this proof also reveals that f will be decreasing the fastest in the direction opposite the gradient vector, which is negative gradient f. And it will have signed magnitude negative length of the gradient vector. So I'm sure some of you have heard of the process of gradient descent, or like how to optimize using gradient descent, especially if you've studied like large language models or machine learning. This is a common technique. Quite literally, it means computing the gradient, taking its opposite, and that will give you the direction of quickest descent. Quickest descent. So remember, the directional derivative actually gives you the direction of quickest ascent. So if you want descent, you got to take its opposite and it'll go down instead. Okay. All right. So now here's another one that I want you to try on your own, and then we'll do it together. Let's let f equal this function. And I want you to find the rate of change of f at the point 2, 0 in the direction from the point 2, 0 to the point 1/2, 2. And then I'll ask you, what direction does f have its maximum rate of change, and what is that maximum rate of change? All right, so ponder this for a minute. All right, say something out loud about what you think, like maybe what you would do first, or something you could answer right away. All right, now try to work it out on your own, and then we'll work it out together in just a moment. All right, here we go. So, okay, so we need to find the rate of change of f at that point in the direction of this point. So we're going to have to compute a displacement vector, first of all. Yeah, that will give us a displacement vector. Then we're going to have to normalize it, and then we can compute the partials and dot them with our normalized vector. Pretty sure that's what we're going to do. So let's see. Yeah, so first we find our vector v, which takes us from p to q, and this is that vector right there. Again, v is not a unit vector, so make sure to normalize it before you proceed. You can find the length using the standard length formula, or the distance formula really. This squared plus this squared, take the square root, and you end up getting 5/2. So that makes our unit vector equal to this. So this is the direction where we want to take the derivative. Okay, now we need some partials. So if we differentiate this with respect to x, we get e to the y. If we differentiate this with respect to y, we actually get the function back again because of the exponential function. Evaluating these partials at the point 2, 0 gives us these. And that means that our gradient vector is just the vector 1, 2. All right, now we dot our gradient with our unit vector to get this, and we get 1. So that's the slope of the tangent line in that direction, 1, going up. Cool stuff. Okay. Now, oh yeah, we're not done yet. This is why you don't want to dust your hands off so quickly. Reread the question before you walk away. We found the direction. We found the direction that f has its maximum rate of change. That's just the gradient vector. Now we need to find the length of it. Oh yeah, and we found the rate of change in that direction. Oh yeah. So we found the rate of change in the direction of our unit vector. In what direction does f have its maximum rate of change? The direction of the gradient vector. Definitely. Direction of the gradient vector. What is the maximum rate of change? We need to find the magnitude of the gradient vector at that point. So we found that the gradient vector at that point was 1, 2. Now we just need to compute its length. And there we go. So that is the magnitude. All right, cool stuff. Okay, next we're going to pivot a little bit to tangent planes to level surfaces. Yeah, I'll just say that. I won't get too bogged down in what I'm thinking here. So first of all, as you may imagine, the gradient vector is astoundingly useful. It's an incredibly powerful tool, in particular because of the result of that previous theorem. So now what we're going to do is we're going to use the gradient vector to easily compute tangent planes to level surfaces. So a good image to have in mind, I have a figure here in a couple of slides, is to think of like maybe a quadric surface, maybe an ellipsoid or something like that. And imagine you want to find a tangent plane to the surface of that ellipsoid. How would you do it? Well, we're going to find out that it's actually quite easy to do using the gradient vector. And I think even one of you was asking me about this in class the other day, about taking the gradient of a plane. And this kind of leads into that idea. So here's how we're going to set that up. Suppose that S is a surface given by this equation right here, or equivalently, you could write it like this. We're actually going to see this structure, something similar to this structure again in 14.8. So in other words, what I'm saying is that this here is giving us a level surface of a function f, right? So remember, f is a function of 3 variables. So when you set it equal to a constant, what you're getting is you're getting a surface in 3-dimensional space, all right? Now what we want to do is we want to find a tangent plane to that surface at a given point. So let P be a point on S, and we're going to let C be any curve that lies on S and passes through the point P. So before I show a different slide here, just ponder this for a minute. Try to visualize this in your head. Maybe I need a new emoji that shows like visualizing something in your head, right? So we've got a point P on our surface, and C is any curve that lies on the surface and passes through the point P, any curve at all. Right, so hopefully you've got that picture in your head a little bit. Now, the curve can be described as a continuous vector function, r of t equals x of t, y of t, z of t. So going back into like chapter 12 stuff, right? Or chapter 13 stuff. Let t naught be the value that corresponds to p, so that when you plug in t naught to this, this function for the curve, it puts you at the point p, all right? Now, since the curve since the curve C lies on S, that means that any point given here by this vector function has to also lie on S. All right, so ponder this again for a minute. Because our curve is on the surface, that means any point on the curve must also lie on the surface, which makes sense. All right, so if any point on the curve lies on the surface of S, that means that it has to satisfy the equation of S, which means if we plug in this point to our function f, this is going to be satisfied. All right? That's the idea. Now, if everything is comfortably differentiable, then we can use the chain rule to reveal something very beautiful. So here we go. We're going to differentiate both sides of that equation with respect to t. So d dt of f, d dt of k, derivative of a constant is 0, so that goes to 0. Now we're going to have to use the chain rule, right? So we're going to use the chain rule and add up all those partials, all those products of partials and things. So derivative of f with respect to x times the derivative of x with respect to t, right there, plus derivative of f with respect to y times the derivative of y with respect to t. There it is. Derivative of f with respect to z times the derivative of z with respect to t. There it is. So there's our derivative after we've computed the derivative with respect to t. Now check this out. There's that structure again. There's that like product plus product plus product plus structure again. We can write that as a dot product. Here we go. Partial f partial x, partial f partial y, partial f partial z. Form a vector out of those components. Dx dt, dy dt, dz dt. Form a vector out of those components and write the whole thing as a dot product, and boom. This is the gradient of f. And this is the derivative of r, right, with respect to t. So we're saying that this dot this equals 0. So what we've really shown is that the gradient of f dotted with the tangent line or tangent vector is equal to 0. But that means that they have to be orthogonal to each other, and that's what this picture is showing us right here. So the dot product of the gradient vector and the tangent vector to this curve was arbitrary, has to be 0, so that means the gradient vector and the tangent vector are orthogonal to any curve C on S that passes through P. Let me zoom in. There we go. All right. So this is essentially what we just proved right here. We found that the gradient of f is orthogonal to this tangent vector r prime at the point x naught, y naught, z naught. All right, cool stuff. Now, the gradient vector gives the direction of fastest increase of f. And, oh yeah, we're getting some intuition here. If we're looking at level surfaces, so, because remember, this is where it gets hard to visualize, because this surface is basically like a slice of a three-dimensional object, right? So since we're looking at level surfaces, it makes sense that the direction of greatest increase would be outward from the surface, right? It's like we're going out of the surface. That's why the gradient is pointing outward. In other words, it's orthogonal to the level surface itself, pow. Just like that. If we move in any direction along the level surface, so if we move in any direction along this surface that you see here, then the value of f doesn't change. That k value does not change, right? And then if we move outward, it'll increase. And if we move inward, it'll decrease. So this thing is basically giving us, well, maybe you can kind of put it together from this picture. This gradient vector is giving us it's giving us a normal vector to the tangent plane, which we're going to get in just a minute. If this is a little bit hard to visualize, let's go down a dimension and look at it in 2 dimensions instead. So take a look at some level curves on a surface generated by a function of 2 variables. So what you'll notice is that, again, the gradient is going to be perpendicular to the level curves. So like here's a picture. I'll emphasize those in just a minute. And what'll happen is the gradient will be perpendicular to the level curve because f would be increasing as you traveled, will increase as we travel outward. There we go. So here is a level curve from a surface, right? You project it down onto the xy plane. Now, if you find the tangent, you get this, but we just showed that the gradient is going to be orthogonal to it, so the gradient is going to point this way. And maybe this will help a little more with intuition if you've ever looked at like a topographical map. The curve of steepest ascent is given by the gradient vector. So as long as you are perpendicular to every one of these level curves, that will be the fastest you can go, right? Let me zoom in a little bit. There you go. Yeah, exactly. So perpendicular to that level curve, that'll be the fastest way you can go. And that's true for every possible level curve. Cool. So that's the idea. Maybe some of you saw this before. I know we don't cover this in Calc 2 at SMC, but some of you might have learned this in Calc 2 elsewhere. If you ever learned about orthogonal trajectories, those are basically what we call gradient vector fields. So you have some scalar function that's basically, here's the level curves of that function right there. In this case, we've got a saddle. And if you look at the gradient at every point on that surface, then what you get are what are called orthogonal trajectories or a gradient vector field. And this stuff is where things get super fun because if you imagine like a mountain pass, This is kind of telling you, this is telling you where the water would flow if it were raining. Although that's a little bit misleading because remember the gradient gives you the direction of steepest ascent. So if you took the opposite, you would get the direction of steepest descent. And so that will really be the direction of the rain. But if you can imagine rain falling on like a mountain pass, you want to know where is the rain going to go? Well, we can describe that. We can describe that with the utmost precision, as precise as you want to be. Okay, now back to tangent planes. So the good news is because we have this gradient vector, it makes it really, really easy to find tangent planes to level surfaces. So as long as our gradient is not zero, then the tangent plane to a level surface given by this formula or something equivalent at a point P is the plane that passes through P and it has the normal vector gradient of F. That's it. What is the formula or what is the equation of this plane? It's this. And so this, I hope, looks really familiar now because I know this is something we talked about in chapter 12, and I know I've emphasized throughout the course. This is the plane. This is the way of describing the plane, and these are kind of like your direction numbers, right? These are the components of the normal vector, and this is a point where you are computing those values, these partial derivatives, and then just set it equal to zero. That's it. That's it. Again, naturally, this generalizes to functions of n variables. I won't do it here, but I encourage you right now to think about it and see if you could write the general formula for a tangent hyperplane to a level hypersurface for a function of n variables. This one was 3. See if you could come up with the one for n, right? There you go. Think about it. Maybe tell yourself what you might have to use. There's a particular notation that could help you out here. And then try to write it down on your own. Okay. All right. What was I about to do next? Ah, yes. Okay. All right. So now that we know how to find the normal vector to these surfaces, we can also describe the normal line. And the normal line is going to look very, very familiar. It's basically going to be the same formula that we saw back in section 12.5, but in this context instead. So the normal line to a surface S at a point P is the line passing through P that is perpendicular to the tangent plane. So very intuitive. If this is my tangent plane, here we go. If this is my tangent plane, and that's my normal vector, the normal line is just the line that passes through P and has that direction. So kind of like we saw before, these are the symmetric equations of that line. You've got x minus x naught, y minus y naught, z minus z naught, and then those direction numbers of the line are given down here. Remember before this was like A, and this was like B, and this was like C? That's what we're looking at. That's what we're looking at. Except now we were able to find those by just computing the gradient. And that's all we had to do. Yay! It's nice. Okay. Yes, so now let's practice. Here's an example that I want you to try on your own. This one's chock full of examples you get to try. Find the equations of all the equations, vector equation, parametric equations, symmetric equations, of the tangent plane and the normal line at this point to this ellipsoid right here. Right, so ponder this for a minute. Okay, now talk to yourself or talk to somebody, say what you're going to try first. What do you want to start with? Right, and now calculate it. So work it out on your own and we'll do it together in just a moment. All right, here we go. So, well, we're going to need to write this as a function of 3 variables first. And this is something we're going to see again when we get to section 14.8. So it's good to kind of take note of it now so it doesn't throw you off so much then. This ellipsoid is equivalent to the level surface given by this formula here. So this is what we're going to call our function of 3 variables. All we're really doing is we're subtracting 3, subtracting the constant, so that this would be equal to 0. So now what we need to do here, we just re-expressed it like so. We need to find the gradient vector at this point. So if we need to find the gradient vector, we got to compute some partials. Here we go. Partial with respect to x, partial with respect to y, partial with respect to z. Now we're going to evaluate each one of those partials at the given point. We got -1 for this one, 2 for this one, -2/3 for this one. Boom. Now we've got our gradient vector at this point, and it's this vector right here. Okay, so what is left? We've got our gradient vector. Now we need to find the equation of the tangent plane. Well, we've got a point, so we're pretty much done. We have the direction of the normal vector, and we have a point, so that's going to give us the equation of the plane like that. Boom. There it is. Oh, I'll remind you all about this. Remember, you do not need to multiply all of this out and combine like terms and write this in standard form. That is not a requirement. That's not necessary. This is a valid form of a plane, and you can just leave it like that. It might feel a little bit weird to get used to now, but this is more informative to us at this point, because you see what happens is when I look at this formula, I can see exactly what the normal vector is, and I can see a point on the surface. There we go. Or on the plane, right? I should say the plane and the surface. So this is actually more informative right now than if you were to multiply everything out and combine like terms. So if you were to do that, these direction numbers, or the direction numbers of the normal line, would still be the same, but you're going to mush together all of the information about the point. And all that information will just get merged into a single constant called d, right? So in a lot of cases, this representation of the plane is more informative and more useful. So don't feel compelled to always write it in standard form. You don't need to do that in every case. Um, Now, symmetric equations of the normal line. Well, oh, did I not? Oh, jumping ahead. You didn't see that yet. I guess I didn't write down the other ones. I guess I should edit this and say symmetric. There you go, the symmetric equations of the tangent plane, since I didn't do the vector equation or the parametric equations. But you could easily deduce them from the symmetric equations down here. But that's what they are. So those are the symmetric equations of the normal line, and that's it. So on that note, let's play. Let's play. So I hope you liked this lecture. Happily, it wasn't super long. Just remember, the gradient vector is an extremely powerful, extremely useful tool. We're going to be using it a lot from now on. And yeah, I guess that's about it. So I'll stop rambling, and I'll see y'all next time.